So thank you everyone for waking up early on the last day of the conference and coming here to hear things. It was an amazing week plus. There were so many beautiful ideas, so many interesting applications. So there's a little bit of pressure, right, to giving a talk on the last day of the conference. However, I will tell you about something that's, I think, new and different from things that you've heard about so far. But it will also feature kind of ideas and pieces from so many different talks, including the Yasu's quantum groups from Wednesday, and then all of the applications. So what I want to tell you about is there will be references and results from work with other people, but the main ideas will be from joint work with Davide Gurinari and our very own Pavel. So I actually want to tell you how applied topology can be used in theoretical mathematics. So I know I have promised applications in cancer genomics and so on, so talk to me after the talk about those. But we have adapted ball mapper tools and enhanced them so that they can be used to study node invariants. What I need to say and make sure that, that it's clear that the tools that we've developed are not limited to applications in theoretical mathematics or, for that matter, not theory. So they're general and can be used as needed, right? But I will also mention how the idea of filtrations can actually be used to analyze not data, which is an example of a really infinite data set, which we don't know how to sample, and it's, well, to my knowledge, impossible to obtain a representative sample, or at least it's impractical. And of course, it's the ball mapper. So we're going to be visualizing our data and exploring it, and it's going to be really high-dimensional data. However, with no noise, right? In the case of non-invariants, right? Because we know how to compute them, and we know how to compute them exactly. So there's no numerical approximations. And then throughout the talk, I'm going to highlight a little bit of hopefully symbiotic relationship between topological and traditional statistical or AI methods. Again, that's maybe more prevalent in other applications, but definitely I will talk about machine learning tools that have been used to study node invariants. But hopefully together, they'll be able to provide a more robust and comprehensive approach. So again, I will tell you about non-invariants, but you don't need to know about them, and you don't need to love them, although they're beautiful. But before I do that, I want to tell you that knots are big data. And we've known that since 1987. There's a theorem of Ernst and Sumner's that sort of says that the number of knots grows exponentially with the crossing number. So there's only one knot with 3 crossings, there's only one knot with 4 crossings, there's 2 knots with 5 crossings. It's growing slowly, right? But when you make it to, I don't know, 19 crossings, there's like 350 million. And that's a fairly recent result by Benjamin Burton and their software Regina that was mentioned in talks on Wednesday. So there's like some serious algebraic topology and manifold theory that's actually used to classify knots. And then there's more. I just don't know how to pronounce this number quickly. Okay, there's also tables of knots, right? Again, the first one was the 70. Well, the first one goes to like really long time ago. But anyways, we have the data, and then again, since knots are intrinsically 3-dimensional objects, once we project them, there's something called combinatorial explosion. Okay, so I'll mention this data set that contains this many knot diagrams, so different ways that you can draw a knot in 2D. It's a 4-valent graph, you just like over/under additional information. But there was like this many of them, not necessarily representing distinct knots, up to actually now 24 crossings. This is the previous work that was used to prove some of the conjectures. Okay, so knots are big data. But then I promised that we're going to work with knot invariants. So let me tell you what a knot invariant is. I think in this language, I mean, knot invariant is just like a feature of a knot, like the way to kind of extract some number from a knot. So it's a function that sort of takes knots as an input and produces some output, which can be numerical, can be a polynomial, can be a group, or can be a whole homology theory. And the rule is that if you have two different representations, two different diagrams, let's say, of the same knot, the way you define your invariant has to be oblivious to different representations. So if you have two knots that are the same, you get the same value out. However, it might happen that two knots that are different will produce the same result. So there are no perfect computable invariants. So again, there's a loss of information, as we know in topological data analysis, like the tools that we're using don't capture all the information, cannot distinguish all of the spaces, so it's the same with knot invariants and knots. By the way, please feel free to interrupt me at any point. I know that I'm covering a lot of ground, So again, there's also many knot invariants. So in addition to having many knots, there's also roughly about 50 knot invariants, and again, they have different types. And there's also software that can be used to compute them, the databases, and then so far, before our joint work with Pavel and David, the approaches were either theoretical or machine learning. Okay, so how do you construct a point cloud from knot invariants? So I'm going to show you a knot point cloud construction from a polynomial invariant. And polynomial invariant is a one-variable polynomial that has integer coefficients. So basically what we're going to do, we're going to take the coefficients and we're going to just like flatten it in a vector. We're going to compute the minimal and maximum powers over all knots, augment with zeros on both sides, and that's our point cloud. So here's an example for very small knots. I'm computing the invariant J. These are all the possible powers of my variable. It's a Laurent polynomial, it doesn't make a difference. But there, so we basically center it around the free term, pad with zeros on both sides, and these are samples of vectors that we get out. So again, the polynomial invariants that I'm going to be talking about that you don't have to know anything about, but they're so-called quantum invariants, and they're obtained using the theory that Yasu was talking about on Wednesday. They're using quantum groups. So for example, this Alexander polynomial corresponds to GL11, and then the Jones for SL2, and so on and so on. But again, we basically have this, hopefully what we're going to get in TDA from Yasu's approach, we're going to have this like very simple invariant that sort of remembers about the algebraic structures that are behind. Okay, so so what I have here, Alexander polynomial for just a circle is 1. For this unique tree-crossing knot trefoil, it looks like this, and then this is the data vector that corresponds to the trefoil. So what we did, we actually looked at all of these 4 polynomials. We constructed the corresponding clouds, and there's a little bit more to be done with complex PT and Havana polynomials because they're 2 variable polynomials. We did the simplest go-to thing to just flatten the matrix and obtain a really long vector. So now we have a lot of knots, we have a lot of invariants, we focus on these 4 polynomial ones, but then actually the dimensions of these point clouds are also very big. Okay, so if we look at knots up to 17 crossings, Alexander point cloud will be 17 dimensional and Jones 51, and then it only gets worse from there. Okay. So I think it qualifies for applications. And so what are the things and types of questions that people who like knot theory are interested in? So again, the reason why we get knot invariants, the reason why we get like topological descriptors is to distinguish, either 2 different cancer types or machine learning algorithms or whatever. So I want to distinguish knots. So how do I distinguish knots? I pick an invariant and see, does it give me different values of my 2 knots? If it does, great, my knots are different. If it doesn't, well, it's like rinse and repeat. Pick a different invariant, compute the values. Are they different? Knots are different. If they're not, pick another one. And so on and so on. So that's one type of question. Can your invariant distinguish a random pair of knots? And then the other one, can I just distinguish all knots, right? or all nodes up to 17 crossing, or 18, or so on and so on. And this is actually very, very different types of questions, and it's a recent result by Danny Tubenhauer and Victor Zhang that actually says that these invariants that I'm talking about will actually distinguish any pair of nodes with probability 1. There's actually, exponential growth, but they will fail miserably in distinguishing all nodes. So as you go along the crossing number, there's exponential decay. And actually we've seen that in our work, and they were inspired by the results that we get. But then there's a very simple question. Let's say you really, really like some particular node, maybe just the plain circle, the unknode. Can your invariant detect that particular node, let's say the unknode? So in other words, if you give me the node, can I tell you for sure when I compute this invariant that there does not exist some other node with the same value of that invariant? And even for just a plain circle, there's invariants that can distinguish, there's invariants that cannot, and there's invariants that we still don't know, right? We believe they might be true, but it's not clear. So for example, things like genus, not floor homology, Hovanov homology can distinguish the unknown. So you compute the Hovanov homology, you get it's like Z and Z in degree 0, or Q and Q if you're working with rationals, and you know it has to be the unknown. However, if you're just computing the Jones polynomial, that was at J in the thing, and you get Q plus 1 over Q, you don't know if it has to be the unknown. Maybe it's some very complicated knot, because we know that it holds up to 24 crossings. There's no knot up to 24 crossings that has the same Jones polynomial as the unknown. But maybe, just maybe, there exists some really high crossing number that's really complicated that does. The community is divided on this question. But I want to show you a picture that's, again, goes back to the quantum invariance, but there's some order between these invariants that I'm talking about. So if I'm looking at the Alexander polynomial and the Jones polynomial and the SLN polynomials, it's kind of, it's again, one variable. You can sort of plug in certain numbers, maybe roots of unity and so on, and see whether they're the same or they're different. Or you can have this anecdotal data. Oh, look, I have these two nodes that have the same Alexander polynomial. Maybe they have different Jones polynomials. And either way, it goes. So the symmetric difference is not empty. Sometimes they're really not comparable. But what we know is that this Home-Fly PT2 variable polynomial is strictly stronger invariant. It's a two-variable polynomial that specializes to the Alexander polynomial when you plug t equals to 1, and to Jones polynomial when you plug t equals q squared. Okay, so we know it's a stronger invariant, so it can distinguish more nodes, but it's also more complicated to compute. So then the question becomes, can we actually tell when we need Home-Fly PT polynomial? By the way, PT is for Przytycki-Traczyk, I have to say that in Poland, and he is my advisor. And the idea is that sometimes you don't. So, for example, the Jones and the Home-Fly PT polynomials distinguish the same three braids. So if you're just interested in three braids, you're good to go with just the Jones polynomial. But in general, there's this hierarchy. And then there's this notion of categorification, which is basically a way, I've talked about it on Sunday, but it's a way to upgrade your polynomial invariant and get a homology theory. And roughly the idea is the same, how you can go from a Betti number to a homology group, right? So homology is factorial, and it has the group structure, but the Betti number is just a number. So all of these theories that are sort of added, right, from here to here, they're homology theories, they're categorifications, and roughly you can compute, let's say, coefficient of the Jones polynomial just by computing the Euler characteristic of the corresponding Hovanov homology. And then you sort of say, okay, this is something you need to prove, but once you categorify it, you actually do get more information. So there are, Hovanov homology is, let's say, strictly stronger than the Jones polynomial, and not floor homology is strictly stronger than the Alexander polynomial. And by the way, these are less than 25 years old or less, right? So it's fairly new development. And then what's really beautiful that I have to kind of mention is that now we went from just having kind of the relations between polynomials that are on a case-by-case basis. So you sort of observe that they're the same for some value and so on and so on, to actually having the tools of homological algebra, right? So now there's a spectral sequence from Hovanov to Nod for homology, and you can use that to obtain results. But then sometimes, again, for certain classes of knots, Hovanov homology is basically determined by the Jones polynomial plus a single integer valued invariant. So anyways, these are the types of questions that I want to understand. But going back to kind of how good are these, the question how good these invariants are distinguishing knots. So it was a big breakthrough that, again, used the spectral sequence argument. It's a work by Kronheimer and Rubka from 2010 that sort of says that Hovanov homology distinguishes the unknot. That's still an open question for the decategorified Jones polynomial. And then there's the work of many, many people through, you know, I stopped somewhere and I apologize if I missed people, I'm sure I have. But there's just like, you know, there's some infinite families of knots, but we're far from understanding 350 million or 1.8 billion knots, right? What they do. So really, really we need results. And I have contributed to this body of work too. There's a collaboration between 5 people that involves at least 2 spectral sequences and 2 homology theories to prove that Hovanov homology, there's no other knot that has the same Hovanov homologies for 1. We can't do that for 350 million knots, right? So what are we going to do? Well, let's look at how, there's the database question as Pavel used to tease me over that. How good are these invariants at distinguishing knots? So, you know, up to 15 crossings. Alexander polynomial actually has only 11% of unique values. Jones polynomial, for which Jones got Fields Medal, is doing somewhat better, but, you know, less than random, right? Less than 50%. And so on. And even if we kind of take them in pairs, we're still barely above 50%. Okay, it is what it is. But we can also take the data approach to kind of look at some really famous and long open conjectures, including Fox trapezoidal conjecture. Again, there's a lot of words here, but all it says is that the coefficients of this one variable polynomial first increase, then they stabilize, then they decrease in a symmetric way. So it's a trapezoid. Okay? And it even sort of says that we know how big the plateau, the stable version is going to be, how long. And that depends on the value of the invariant that's called signature. So notice here that this conjecture was only for alternating knots. That's a very prevalent class of knots for small crossing number, but in general, it's like a tiny fraction of knots. And then, you know, this conjecture has been open for a long time, so it's been proven for various classes of knots, not for all alternating. But let's see what we get. Oh, I'm missing a slide. Oopsies. Okay, so but if we look at if you look at it on the database question, you can actually see that out of all of the knots up to 18 crossings, it of course there's no counterexample. It holds for all alternating knots, but it actually holds for about 88% of non-alternating knots. So it's like one of the things where it's a kind of the opposite. Like knot invariants kind of are not really good, at least the ones we have now, at distinguishing knots. But this conjecture has been made like in a kind of like very modest way, right? To hold just for alternating knots, where it holds for like in much greater generality. Actually, it's more true than not, okay? So it fails for about 1 million knots out of 10 million. Okay, so these are some of the things that kind of data approach can give us, and I was really blown away by these results. So, of course, once there's big data, I think there's AI tools. And this is, again, an incomplete list of some of the results where various AI techniques have been used in knot theory. And again, these are the published dates, so it goes far beyond 2019. I mean, further back than 2019. So somehow the idea was like, well, some of these knot invariants are actually NP hard to compute. Can we use neural networks to predict them? again, the work of Jajala, Karp, and Parikar, they're actually addressing another really famous conjecture. There's a work of Craven, Hughes, and Jajala and Karp, which actually relates to our work, but we published later, but we preceded their work, about illuminating new and known relations between non-invariants. And again, these are some of the famous conjectures attacked by various tools. So let me kind of focus on this work here. So these are like two papers. One is a Nature paper, one is a geometric topology paper. So the idea is, I mean, the title of the paper is Advancing Mathematics by Guiding Human Intuition with AI. So I think the message from the paper was that you can understand and discover new relations between non-invariants by using some tools. Again, this is a paper from 2021. They've used saliency maps to sort of determine how relevant are values of one invariant to other. And somehow the premise is that if I think that certain invariants, the values of certain invariant are important for the values of this invariant, that somehow there should be a theoretical relation. And again, this paper, again, it's a collaboration of Juhasz, Lackenby, Tomashev, and people from DeepMind. The idea is that one of the relations that was discovered, they were actually able to prove it and get a theorem out of it. And again, my understanding is that recently there's a lot of results in enumerative combinatorics, number theory in particular, that have been attacked using these tools. However, you know, when you look at these papers here, there's been a tremendous progress. So they have been able to rule out certain potential counterexamples and prove that they're no longer counterexamples. And for example, for the slice ribbon conjecture that I'm mentioning here, that's been open since 1962, they were not able to prove it, but you know, it's like 98% theorem, right? Using the tools so far, the tools that we have available so far. So, and again, there's like this gigantic work that ran like 200,000 different examples trying to uncover pairwise and triple relations between non-invariants. And you know, they do get some results, but there's like very few understanding of like why and how and what the relation exactly is. So you know, it's like 72% there's a relation between these invariants. So which 72, what do I do with it? What's the exact relation, and so on and so on. Okay, so again, with AI techniques, there's kind of two main ideas behind it. One is to kind of predict the values and find the relations, which finding relations is what we're going to be working on. And then there's like, of course, proving conjectures, which is also what we're going to try to contribute to using TDA tools. Oh, there's the data. Sorry, I somehow messed up my slides. I apologize. But here are the actual numbers for that Fox trapezoidal conjecture. I think I said 88, it's 85. Okay. Okay, so let's move on. So TDA tools, I don't think I need to talk to this audience about them. We've heard so much about multidimensional persistent homology and mapper type tools. The first thing that I'm going to do, I'm actually going to combine the filtration idea from persistent homology with PCA. Why? Well, because I have my data organized by the crossing number, and I know that I don't have a representative data sample. So maybe, just maybe, if we do PCA on crossing number n, then n plus 1, n plus 2, and so on, and we get some sort of stability, if we observe something, we can hope that that's actually an essential feature of the knot data, and it will persist for higher n. So again, this is a joint work with actually Mustafa Hajij and Jesse Levitt. So if you look at the Jones polynomial data, and I know that this doesn't look very three-dimensional, but this is a three-dimensional projection of 51-dimensional point cloud. And what we've decided to do is to actually look at something we call the dimensionality of the point cloud, just the smallest value d for which the normalized explained variance for the first d principal components gives you 95% explanation. And it turns out that this Jones data, again, goes from 51-dimensional to maybe 3 or 4, maybe 3, but maybe slowly growing. if you look at the stability of the principal vectors, maybe in the of time I just focus on this one here. You can sort of see that the first principal component is very stable, second one less stable, third one less stable. We actually understand why these bumps happen. It's for parity reasons. But you can sort of see that for whatever unknown reason, it's just like a very good development that the more significant the component, the more stable it is across this crossing of filtration. Okay, so this is for the Jones polynomial. If you look at the Alexander polynomial, this is a two-dimensional projection. Actually, one dimension explains 98% or 99% of the variance. So somehow the idea is that the Alexander polynomial is one-dimensional. Again, it's just a data point. What do we do with it? So actually, to analyze this more, we kind of went to the wall mapper. Again, I don't think I need to explain to this audience. This is just for completeness. The motivation between the mapper constructions, which just comes from the read graph. So basically, you have a manifold and a function that's called a height function, so it's R. And the read graph construction basically says 2 points on my manifold will be identified if they're the same height and they belong to the same connected component of the inverse image of that one. So okay, so for, again, this height here, the whole circle will just become a 1 point, but here, because we have the same height but two different connected components, we're going to have two different ones. Okay, so then again, the read graph is just a quotient space under this equivalence relation. Great. Let me go to the example that I'm going to get back to because it's very simple. So if my data is just sampled from the letter y, and I have a height function, and for the mapper construction, I'll look at the range, I'll pick intervals of certain lengths, I choose the amount of overlap, and do the mapper construction kind of the same as the read graph construction. So at this level I get two different clusters, at this level I get one cluster. Great, so again, point cloud, get the cover, each element of the cover becomes a vertex. If two elements of a cover have overlap, we put an edge. And then again, the bonus feature, which is always good, we can color. If you have some other property, and in the world of knots we have many different invariants, right? We can choose how to color the vertices of the graph based on some other property, right? And that's what we do. Okay, great, but we are going to use the ball mapper. That's really convenient for theoretical mathematicians because it makes you pretend that you did not make choices, although not making a choice is making a choice, right? So here the input is point cloud x and a single parameter epsilon, just the radius of your point cloud. And then the way that you the trade-off that you do for not making those choices is you have this different construction where you sort of pick certain subset y that's labeled by these red points and actually emphasized by blue arrows, sort of subset of your points such that the epsilon net construction gives you a cover of all of the data. Okay, so and then you just proceed as you would with the standard ball mapper. Right, but of course we don't know. I mean, there's like a choice here that's heuristic, we don't control it. Okay, any questions so far? Okay, so here are the results. So if we use the ball mapper construction on Jones data, there's at least two things that we should worry about immediately. So one is the stability with respect to epsilon, our only parameter, and the stability with respect to the filtration that comes from the crossing number, that comes from the knot data. So again, we were happy about it. I'll refer all the questions to Pavel. So knots up to 15 crossings, 16 crossings, 17 crossings. Again, maybe let me just point out that the difference in data, when you go from one number of crossing to the next, it like roughly, the size of data of the point cloud increases like tenfold. So the really 17 crossing knots will dominate the point cloud once you kind of add them. So I think it's like really nice that we have kind of this, observing this similar kind of star-like structure. And then, again, this is what you get when you sort of zoom in or zoom out for different values of epsilon. And again, the color that you see here actually comes from an invariant that's called signature. It's just an integer, and even an even integer that's associated to knots. And we went to it because I was inspired by the Garufolidis conjecture. So again, this is one of the conjectures that's proven for all knots up to 8 crossings and for all torus knots, that sort of says that not just the Jones, but the whole family of Jones polynomials actually corresponds to coloring by different quantum invariants, determines the signature of a knot. But for so-called simple knots, that's a condition that it depends on the zeros of the Alexander polynomial, et cetera, et cetera. So the details are here. So again, it's a very important but modest conjecture in some ways, right? And what we did, we sort of said, okay, what do we get if you focus just on the first Jones polynomial, the one colored by SL2, and all knots? What are we going to get? How much does the Jones polynomial knows about signature? So we wanted to kind of do that, and so the coloring here actually reflects the coloring by the average value of signature. Okay, and then just to kind of be completely transparent, right? Jones polynomial doesn't determine the signature. It fails miserably. It fails in many different ways. You can have pairs of knots. You can have many knots with the same crossings, with different crossings, all sorts of things. So it's not a theorem, right? We know that it fails. Again, we can, just stay with me, I'll get back to this, but we can sort of color the Jones ball mappers with other invariants. So for example, this is coloring by the determinant. It's not showing very well, but the values of the determinant grow as you're moving away from the central node. Here you can actually see that there's small but somehow very important or go-to class of knots that are called alternating knots. They're all the way out here in the flares, but then in the middle there's a mixture between alternating and non-alternating. And then if you color by signature, you can sort of see that there's certain flares, like this is like 2, this is 6, this is 10, and then on the other side, again, this is an arbitrary bedding, but 8, 0, 4. So then when you look at this, you're like, oh, well, it looks like signature mod 4, if it's equal to 2, it's on one side of the messy center, and then the 0 value mod 4 is on the other side. So there are some things that you could sort of observe when you do exploratory analysis. If you do the same thing for the Alexander data, well, look, it turns out to be one-dimensional, just like our PCA kind of suggested it should be. Determinant also increases as you're moving away from the center, although you have only 2 flares, it's a linear structure. Again, a mixture of altering, non-altering here, just altering in the ends. Signature, no signal, right? But signature mod 4 still works, right? So there's a messy center, and then 2 mod 4, 0 mod 4 on these sides. So first thing that I want to introduce is actually something that's called a equivariant ball mapper. The idea is that I know as a knot theorist that there's various relationships and symmetries that Jones polynomial or Alexander polynomial exhibit, and I would love to see that reflected on the ball mapper graph. So again, this is a ball mapper graph for the Jones without the symmetries. This is with symmetries. So what David and Pavel implemented is this idea that if you know that your data has symmetries or should have symmetries, right, you can sort of incorporate that in the ball mapper construction. It's actually not so easy to do on a mapper construction. So you basically have a point cloud, then you have some action by a finite group G. That needs to be isometry. You can live this action to the ball mapper just by saying, well, if I pick a point to be a landmark, I'll pick all the elements in its orbit to also be landmarks, so then the structure will be reflected. Okay, so simple idea that gives us good results. I want to illustrate this on my favorite example. I hope everyone played tic-tac-toe. I'm not going to be talking about strategies. It's a pretty simple game. I'm going to look at the end game results, right? So I have game in progress. This is X wins the game. This is the game that's like a tie. So I'm just going to turn it into a vector in 9-dimensional space by saying, 0 is a -1, X is 1. If there's no X or O, like here, I'm just going to put a 0 there. And the idea is that, of course, as we all know, there's going to be 958 vectors, and we all know that it doesn't matter which corner you start in. If you start in the corner and there's like symmetric games, the game doesn't depend on, like it's invariant under the action of a dihedral group, let's put it that way. Okay, but we need to I would love to see that within the data. So when we use the equivariant ball mapper, this is what we get. The value for epsilon, for those who are like really into it, is 2.5. And what you can see is wins and losses and ties are their separate components. Again, for epsilon 2.5. And then if we do equivariant ball mapper, we can see, well, we still get the same cluster, it's the same value of epsilon, but we can sort of see that there's symmetries, and in particular, you can sort of see the symmetries in both wins and losses. But of course, there's no symmetries that will take wins to losses, right? You cannot act by the dihedral group and make yourself win if you lost, right? And then, because Davide is amazing, he actually went like deeper into the thing, so he actually colored the tic-tac-toe ball mapper with actually the elements of the orbit. So if you see, this cluster here, it's like the maximally symmetric one, so they're all together, but we have a cluster here that says there's like 4 of them. I don't know, where's the 4th one? Here's the 4th one, and so on. So we can actually see the structure of our results, and we can sort of see how the different types of winning and losing sort of can be related to each other. And then we can actually prove that for epsilon equal to 2, we are going to get a picture where all of the wins are connected, all of the losses are connected, because we can actually prove, we can find a path between each winning configuration to each other winning configuration that's length 2. And then we can prove that there's no path of length 2 that contains of steps of length 2 between wins and losses, or wins and ties, or ties and losses. But then things change, right? So epsilon equals to 3. Actually, it's the wins and the losses that get connected, and ties are still separate. And it's a fun exercise to do and to sort of see why. So maybe if you're bored, you can think about it and tell me at the end. It's like not hard to figure out. Anyways, for 4 and then for 5, everything gets connected. Okay, back to knots. Gunnar actually talked about it, and I think called it double mapper in the case of mapper algorithm. We call it mapping mappers, and it's the idea is that you can visualize or compare relations between the two really high dimensional point clouds by comparing their ball mappers. So how are we going to achieve that? So if we have a model of a space X, and we know that there's a function or a relation, we can color the output. So here, if I have a point cloud X and a point cloud Y for some high N and M, and I know that there's a relation between them, I would like to be able to see the shadow of that relation on the ball mapper graph. So again, there's a lot of words here, but basically the way you do it is you construct a ball mapper for the first point cloud and a ball mapper for the second point cloud. And then you're basically going to pick a cluster, a vertex in your ball mapper graph, and then of X, and color the ball mapper graph of Y by the percentage of knots in each cluster that come from the chosen one. Okay, it's going to be much easier to actually illustrate it, but basically the idea is that for each vertex in the ball mapper of X, I'm going to get the coloring function of the ball mapper of Y that's going to reflect the distribution of these. Okay, so here's a picture, and again, Interactive pictures are much better than the still images, and they're available on the Dioscuri website, so please go ahead. So the idea is that, let's say if I'm interested in this collection of clusters on the Alexander ball mapper graph, I can actually get the coloring of the Jones ball mapper graph and sort of see what the distribution is like. And kind of get the region correspondence. We can actually do the same, and now for the first time I'm actually showing you ball mapper graphs for the Jones, Home-Flight PT, and Hovanov polynomials. Again, these two are two variable ones, and stronger than the Jones, right? So again, if you ignore the coloring, maybe a better data analysis person would know better, but when I look at these, I would be like, oh, they look very similar. They all have some flares. I can probably find a comparison between flares. But it's actually the mapping mapper construction that allows us to sort of realize that if I look at this messy central core, and I map it using mapping mappers into the Hovanov ball mapper, you see a better differentiation, but they're still just the central, they're all in the center of the ball mapper graph. However, if you pull it to the Home-Flight PT, you sort of, again, I think it's harder to see, it looks better on my screen, but they actually got distributed throughout the whole flare. So the structures, although they appear similar, the correspondence is very different. And actually, as I'm going to show you later, I mean, again, the relation between Hovanov and Jones is the computing the Euler characteristic, but the relation between the Home-Flight PT and the Jones is actually highly nonlinear. So again, that's reflected and detected using mapping mappers if we did not know what was going on. Okay, but this correspondence between the Alexander and the ball and the Jones ball mapper actually gives us this beautiful correspondence that if you take the rainbow gradient on the Alexander, it actually, that's somehow linear, it actually introduces the linear structure on the Jones ball mapper. And that actually helps us understand the PCA results. So what we've done, we've actually computed the correlation, and indeed, the PCA doesn't tell you what this dimension, the first principal component vector, corresponds to. But now we know that it's this value of the determinant, another not invariant, and then the value of that same value of the determinant gives us one of the directions in the Jones point cloud. So basically, we know that there is a shared direction between these two point clouds, and it corresponds to another not invariant. And then you can do this for other not invariants, and thanks to Davide, we did. And then we tried, so you can see like pretty pictures. I'm not going to go into details, but anyways, the top row is the PCA projections into 2 dimensions, so the most two principal components, and then the bottom row is the correlation between the first principal component and the determinant. So it works really well for the Alexander data. It works well for the Jones data. It works somewhat well for Hovanov, and then it fails for our other invariants, which is okay. But we can do things like that. And then thanks for the time difference between Europe and the US. I woke up to the question of what does the invariant know about the signature, and by the time that I actually managed to look at it, I had a theorem waiting for me. So Pavel and Davide ran, they sort of noticed that there's this messy center, but that doesn't distinguish signature mod 4, but again, we collapsed the data from 17 dimensions to 1 dimension, or from 51 to 1. So it's not surprising that there's some loss. So they ran SVM, trying to find a hyperplane that separates knots with these different values, modulo 4. And the linear SVM classifier on the Alexander data actually returned the normal vector that corresponds to evaluating Alexander polynomial at -1, which is the determinant. However, it failed to converge on the 51-dimensional Jones data. But there's the correspondence, right? This correspondence doesn't lie, right? So we had to have the theorem. And indeed, what they did rediscover the theorem. And I think Pavel did not talk. It was good it was weekend. I think Pavel was very upset, but by Monday or Tuesday, it was okay. So anyways, I think it's very exciting. I wish we discovered a new theorem, but again, hopefully it's just a matter of time when we're going to discover new theorems. We did rediscover that one that was well known. It's a folklore theorem that sort of says that, you know, again, if you evaluate either the Alexander or the Jones polynomial at -1, it will sort of detect the value of the signature mod 4. Okay, so this is like one thing that we got. The last tool that I want to introduce is the idea how we can use ball mapper to kind of improve this restriction that the height function in mapper goes just to R. So it would be lovely, right, if you could do it into even R2 or maybe even some higher Rn. But again, if you want to have a map that's a cover with k intervals, but now in n-dimensional space, that would require k to the n elements, and they're just not computationally feasible. So the idea that we had is something we call now mapper on ball mapper construction, which sort of says we'll construct a mapper of x using the relation between x and y as a length function, and then we're going to kind of get the ball mapper as an overlapping cover of f of x, and then go from there. So let me illustrate that here. Again, don't laugh. It's the running example. It's not high dimensional. But let's say I have a high dimensional point cloud that lives in 2 dimensions and has 6 spikes, and then not so high dimensional, but still high dimensional point cloud y that has 3 spokes, right? And then the mapping is a very simple one. I'm going to collapse the flares with the same color into one. Okay, so there's some collapse happening there. So again, I have the map, right? So in this case, it's just indicated by the color. So what we're going to do, we're going to say, okay, this is lower dimensional, so I'm going to construct a ball mapper of the lower dimensional thing. And then I'm going to use this correspondence F to pull the cover of the lower dimensional point cloud into the higher dimensional point cloud. Okay, so that's happening here. So I'm illustrating, I'm pulling, if I pull this element of the cover, it's going to have only one preimage in the center. But if I pull back the blue one using the preimage, you know, like using F, I'm going to get these 2 different elements of the cover. And then I'm just going to pretend, I mean, I have a cover, I'm just going to do the mapper construction, right, the reef construction, and that's it. So basically the idea is that if you have this relation, then you can use the ball mapper graph to obtain the cover of the original higher dimensional data set that somehow captures or carries this point of view of this lower dimensional point cloud. So it's not arbitrary. And I think that's beautiful and perfect for the data that, again, I'm interested in, the knot data. So here's my setting. Again, just a different diagrammatics. But we have knots, and to each knot I can assign many different invariants, but in particular the Alexander polynomial, the Jones, and the Home-Flight PT. And here's the Alexander ball mapper, here's the Jones ball mapper. I can construct the ball mapper here too, okay? But somehow the idea here is that I also know these specializations, right? I know how Home-Flight PT specializes to either Jones or Alexander. But let's say Alexander is only 17 dimensional, but the Home-Flight PT is 152 dimensions. Or Jones is 51 dimensional, Home-Flight PT 152. So what we do, we can construct the ball mapper for Jones, pull back the cover to get the cover of the Home-Flight PT, and see what this map from ball mapper graph looks like. So here's an illustration. I know that I'm getting closer to the end. This is the Jones ball mapper. You've seen that one before. This is the Home-Flight PT ball mapper. However, when we do map from ball mapper construction, we're somehow constructing a graph that's mapper-like on the Home-Flight PT data, but somehow with the viewpoint of the Jones polynomial. Okay, to me this was very exciting because the flares in both the Home-Flight PT and the Jones ball mapper are colored by the invariant that's called signature. I talked about it. However, when we do map from ball mapper construction, we get flares that look a little bit different, and they're no longer determined by signature. However, they're actually determined by the categorified invariant that's called the Rasmussen S invariant. So anyways, these flares now and they'll be colored by a different invariant that's actually coincides with the signature on the alternating node, but it's very different, and it's exciting to know when they're different, when they're not. Okay, so what I'm trying to say is that we get interesting insights in knot theory based on this. One interesting feature of the mapper and ball mapper construction that can actually also help you understand the data is that you can now go back to the point cloud of the lower dimensional data set and color by the cardinality of the fiber, right? So you pull back the cover, but now you can sort of say, okay, but look, when I look at the Jones ball mapper, again, the lighter the color, the more of a injective map I get, right? But here, I can see that this huge cluster actually has, a lot of elements in the preimage, which again is somewhat not surprising. But anyways, what this is kind of telling me is that roughly each cluster of the ball mapper on Jones basically has all knots with the same Jones polynomial, but also maybe ones that are similar. And somehow this picture here is telling me that on these knots that are contained on the outside, the Jones polynomial and Conefly PT polynomial do equally well. Which is, again, the question that's interesting to me, and I would love to understand and characterize the properties of those knots. However, these central ones, Conefly PT will do better. And again, we know that there's this spreading into the flare. Okay, summary, ball mapper does provide a way to visualize high-dimensional data, but you knew that in any metric space. We have some additional things that have algorithms that have been inspired by applications in knot theory, but not limited to it. So equivariant ball mapper, if your data has observed or assumed symmetries, you can use that one. Mapper on ball mapper, it's kind of a hybrid between the mapper and the ball mapper construction, right? You use ball mapper to obtain the cover, but then you just do the mapper construction. But it's somewhat computable, right? It sort of gives you, if you have this additional information about the relation between the two-point clouds, it gives you a way to kind of get a higher dimensional lens function, or a lens function with a higher dimensional range. And then mapping mappers, I think it's an analogous to, again, the double mapper that Gunnar mentioned in his talk. It allows you to visualize maps and relations between point clouds. Okay, I can end here, but I will not. So Davide has the code. It's available on Zenodo, on the Escuri Web Center, and if you like to play with these, there's interactive versions of all of these things. But we did actually get some insight into this Garofaludis conjecture and some other ones, so I just want to quickly kind of go over these results that are not theory specific. So remember, the conjecture says that all the color Jones polynomial determines signature for some knots. And we are just looking at the Jones polynomial on all knots. So what you see here is the hypothesis that the Jones polynomial determines the signature for knots with sufficiently large determinant, which means far away from the messy center of the ball mapper graph. And again, what I like about knot theory is that this large determinant, we kind of obtain this combinatorially by plugging in a value. It's actually the norm of the Jones, the order of the H1 of the double branch cover of S3 over the knot K. Anyways, there's a lot of information that's topological here. So what you see here is the two-dimensional PCA projection of knots that have determinant higher than something, and this is just the normalized version of it. And what you sort of see is that the perfect separation between Jones polynomials of knots with different signature. So again, that's something to look into. Another thing is to sort of say, well, how well will the Jones polynomial predict the values of signature? And again, remember, if the Jones knows about signature for alternating knots, it completely determines this fancy category quantum invariant called homology. And it sometimes does. Again, these knots here, these points here tell you for sort of they determine when this prediction is kind of perfect, kind of 100%. But what's really surprising, and I still don't understand, is that Jones predicts signature better on non-alternating knots, which again, from theoretical point of view, is really surprising. from data point of view is great news because most nodes are non-alternating. So again, something to look into. Another thing that we discovered is that, again, a property of the Khovanov homology is that it lies on a certain number of diagonals. The support of Khovanov homology is given by a certain number of diagonals. And if you color Khovanov ball mapper by the diagonals, oh look, the flares actually correspond to diagonals. But okay, that makes sense because we're working with Khovanov data and it knows about Khovanov diagonals. That's great, but when we use ball mapper constructions that we have, somehow Jones polynomial, which is just a decategorification of Khovanov homology, still knows about them. But it shouldn't, it's just a polynomial, right? So anyways, these are some interesting things. Just to sort of say the sampling issues are real. The sampling problems here is really prevalent. So the ideas from the TDA and the persistent PCA were really working. I think we're discovering something that should be generalizable. So you can sort of see 12 crossing nodes all the way to 17 crossing nodes. These are the distributions of the determinant. And you can see that the joint gray distribution, here it's kind of a mixture between the two, but here it's completely dominated by the non-alternating nodes. And the alternating nodes have this like Gaussian type distribution that's sort of irrelevant. It sort of works with the tail. And just to wrap things up, this is the picture for the table that I had in one of the first slides. How good are these invariants at distinguishing nodes? Okay, and again, this is the corresponding graph. So here you sort of see that exponential decay. Right, so there's no hope in graph theory. Actually, you know that the Tott polynomial is conjecturally a really good proxy for non-isomorphic graphs, meaning that the probability that two independently chosen random graphs have the same Tott polynomial goes to 0. But for us, there's no hope to do that. There's this exponential decay. But then you can also notice that if you look at the purple line, which is this one, it actually coincides to Alexander plus Jones line, which is the green one. So some of the idea is that out of potentially infinitely many specializations of the home-fly PT polynomial, just these two work really well on data, at least for 17 crossings. Well, we can sort of apply the ball mapper on it, and again, you can see the ball mapper from Jones and the home-fly PT, and this is Alexander plus Jones. You sort of notice the more elongated features and so on and so on. You can go into this. But together with Aldo Guzman, Ernesto Garcia, and Edison Vasquez, we sort of looked at this data from the AI point of view. So the idea is like, can Alexander and Jones, they're both one-variable polynomials, predict the values of the home-fly PT? Okay, they tried it straight. They tried it from latent representations. They get some accuracy and some mistakes that are good. But what's interesting is that based on the insights that we've obtained using the ball mapper, we actually conjectured that the error in this model is determined by the signature. They've tested that, and basically the results were that the signature relates with the variation in prediction error that can be detected from the latent space. So again, I'm not an AI person. I would love to know more, but the idea is that somehow combining these two tools sort of helped identify the meta variable. Because again, signature is not contained in the data. So this is not like sampling outside of the distribution, right? But we're really able to find and explain the value. Okay, if it's not clear, I think there's a lot of potential for using data analysis in theoretical mathematics. In particular, in knot theory, I think there's a lot of information that's contained in the statistical nature of these point clouds that arise from invariants that has been underlooked in the history of knot theory. I would love to know what types of results can be rediscovered using these tools. And again, I'm super excited about integrating topology and the AI tools. I want to thank you all. I would like to thank the organizers, all of the organizers, and the Pavel organizer for sending the notes in Poznan. I'm still hoping that some of you will send me more of them. And I would love to thank the NSF and the Dioscuri Center for supporting this collaboration. I've actually spent my sabbatical at the Discovery Center that's funded both by Max Planck and the Polish Institute for Mathematics. And again, thank you all for sticking out through this lecture that was, I think, a little bit different than the rest. Thank you.
Thank you.